Hello, welcome to another video. This one's going to be focusing on Atwood machines. Atwood machines are just sort of a fancy name for situations where you have maybe one, maybe two masses, forces involved, obviously, and there's typically some kind of pulley. So there could be one pulley, two pulleys, three pulleys, all kinds of situations. But we're just going to go over sort of the most basic situations you'll see and how to solve them, right? So you can actually figure out a whole bunch of stuff about these situations, like acceleration, the tension of the rope involved, and that sort of thing. So let's just dive into some problems. But in essence, the steps to solving these always begin with Newton's second law, right? Newton's second law says the acceleration of a system is the sum of the forces of the system divided by the mass of the system. And remember, you can apply Newton's second law to multiple objects treated as one thing, one system, or you can apply them to individuals. So I'll kind of be able to show you all both. So we have an Atwood over here, and you can probably guess already what is going to happen if I were to release these masses, right? You would probably expect the heavier mass to start to sort of move this way, right? And then in a similar fashion, this guy will start to move up. But we want to be able to quantify exactly how this is going to happen. And again, your intuition might say, well, they're going to accelerate as well. They're not just going to go at some same speed. And you would be right. But again, we want to quantify this. So what is the acceleration of the system? Of both of these masses, right? Now remember, they're connected by this rope, so they're moving sort of in tandem with each other. So whatever the acceleration of one of them is, the other one should have the same sort of magnitude acceleration. Now I'm going to do something kind of weird. I'm going to call this sort of the positive y direction going up only for this mass. And then down here, I'm going to call this the positive y direction for this mass. And the only reason I'm doing that is so that when we solve for the acceleration for each of them separately, that those accelerations are going to have the same sign. And it'll make some of the calculations a little easier. All right, so let's begin with some free body diagrams. So I'm going to call this mass 1, this mass 2. So for mass 1, we draw a dot. What forces are acting on it? We just have tension and gravity. And in this case, we can sort of intuitively tell that the force of gravity is going to be bigger. Right? So you could even draw it a little bigger. So let's apply Newton's second law to this situation. So we have the acceleration of mass 1 is going to be equal to the sum of the forces. So in this case, that would be tension minus the force of gravity on mass 1 divided by mass 1. And we don't know the tension force, but we do know Fg would be the mass 15 times roughly 10. So we would say 150 newtons divided by 15. All right. Now that's an equation with two unknown variables, so we can't solve it. We need another equation. So this is where the free body diagram for number 2 comes in. So for 2, we would expect 2 to accelerate upward, right? So in 2's case, you've got the same size tension force going up, but the force of gravity is much smaller, right? So we've been talking about Newton's third law. These would be called third law pairs, right? They're showing up in different free body diagrams, and they're equal and opposite. Well, in equal and opposite because my coordinate systems are flipped for each of them, right? So even though they're pointing the same direction in the free body diagrams, they are technically equal and opposite. But anyway, the acceleration of object 2 in this case would be, now keep in mind, right, my coordinate system, I'm saying the positive direction is down. We need to account for that. And if the positive direction is down, I need to be calculating the force of gravity minus the tension force, right? Technically, the tension force is going in the negative direction. If this is too confusing, I'll show you another way you can do this problem that doesn't involve flipping your coordinate system. But anyway, A2 is going to be force of gravity, so 50 newtons, minus the tension force, divided by 5. Cool. And because of the way I flip my coordinate systems for each mass, we can essentially say that the accelerations are equal to each other, right? So notice what I have here. This is a system of equations, essentially, right? Two unknown variables. At this point, we could just call these just A, right? So this is just A, it's just A. And then we have T and T, right? So we can solve this system. Let's first solve for T, right? So what we can do is we can set both these equal to each other. And we'll get T minus 150 over 15 equals 50 minus T over 5. And this will give us the magnitude of the tension force. So if I multiply both sides by 15, I'm going to get 150 minus 3T. Then this will become 4T equals 300. That means that T equals 75 newtons. Cool. And so now we can see, right, like the force of gravity for this lighter mass would be 50 newtons, and that's why it accelerates upward, right? The tension force is greater. Whereas for the first mass, the force of gravity is bigger than the tension force, so it accelerates downward. So that's accounting for why the motions are in different directions. And then we can also use this tension force to solve for an acceleration. And I can use either one of these equations, right? So maybe I'll use this one. A equals 50 minus 75 over 5. So the acceleration, the magnitude of the acceleration of either mass is going to be, looks like negative 25 over 5. So that's negative 5 meters per second squared. Cool. Cool. Now, those are the answers. Those are correct. But I do want to show you maybe another way to tackle this problem. So this is kind of more of a system-based approach. This is where you kind of do something a little weird here. Imagine taking my 15 kilogram mass and my 5 kilogram mass and taking this situation and sort of stretching out the rope horizontally, like this. And thinking about where the force of gravity vectors would be acting on this system, if we sort of look at it this way. Right, remember, over here, force of gravity vector on this mass is going down. Force of gravity is going down over here. Right, actually, this one should be a little bit bigger. But the idea is, if I took this system and I sort of made it completely horizontal, I would actually have FG1 going this way and FG2 going that way. Let me move this somewhere else. And so the reason why we might do this is because now we can treat this sort of as one object, right, that's being acted upon by two different forces. And we can use Newton's second law one time, right? So the acceleration of the system equals the sum of the forces divided by the mass of the system. Well, in this case, the mass of the system is now 25 kilograms. Now, Fg2 was the force of gravity on the second mass, right, which is 50 newtons. So if we say that this is like the positive x direction, why did I write it that way? Plus x direction, we would have 50 minus 150, right? That's the other force of gravity, right, acting on this system. So this is negative 100. Negative 100 over 25, which is negative 4 meters per second squared. Let's see, did I do something wrong here? Oh, that's my bad. Whoops. This should be 20. This should be 20. So that makes this negative 5 meters per second squared. So we get the same magnitude answer. It just sort of, looks a little different. But we essentially get the same acceleration. Now, because we've treated this as a system, right, the tension forces are internal to the system. And so you really wouldn't be able to find those unless you did Newton's second law on one piece individually, right? So that's the one drawback of a system-based approach. Let's maybe try another one. And here I've sort of given you two different situations. One is an Atwood machine where I have a mass at the end over here, whereas in the second situation, we are pulling with a force of 100 newtons. Now you might notice for this mass, the force of gravity acting on it is also 100 newtons. Right, so really the million-dollar question is, do these situations, they are slightly different, but do they function in the same way? Right? Do they result in the same acceleration? So same acceleration. You might want to pause the video and just sort of think about that question for, about a minute or so. Think about, will they accelerate the same way? And we're going to find out in a second. Okay, so let's try this out. Just to save time, what I might do, the systems-based approach is a little bit quicker. If I had to bet money on it, you guys probably would prefer this sort of method. So I'm going to take these Atwood machines and essentially stretch out these things completely horizontal. And I'm going to think about where those force vectors would be acting, right? So there would be tension here, equal and opposite tension there. For the other mass, this first mass, there would be a normal force, force of gravity. But these two, we know, have to be equal and opposite, right? Because the mass is not accelerating up or down. If anything, it's just accelerating to the right. For the 10 kilogram mass, right, this force of gravity vector here becomes this force of gravity vector here. Right, so if I take a systems-based approach, the acceleration of the system, right, this overall system here, the forces that are external to it are what we're going to put in Newton's second law. Now notice in the net, right, this force, this normal force and this force of gravity essentially cancel each other out. So really the only force we know is going to actually show up in the net force is going to be this force of gravity here. All right, so the acceleration of the system is going to depend on the force of gravity, but keep in mind, this force of gravity was calculated only for the 10 kilogram mass, right? So in the sum, it would only be 100 newtons of force divided by the mass of the system. The mass of the system is 25 kilograms. All right, so this is going to become important later on. So the acceleration of my system is 4 meters per second squared. Okay, cool. Now let's do the same thing except with this situation over here. So I have 15 kilograms. I'm going to stretch it out horizontally. And then I have an applied force of 100 newtons. So this is being applied to the end of the rope. We know that because of Newton's third law, this means there must be an equal and opposite tension force here of 100 newtons as well. And because of the way tension works, that means equal and opposite tension is being applied at the other end of the rope, also equal to 100 newtons, to this mass. So for this situation, we don't even need to think of a system. We just sort of just run Newton's second law on this mass here. And this is really the key difference between the two. The acceleration of the system is the sum of the forces, in this case also 100 newtons, but divided by only 15 kilograms. And so this is going to give us, it looks like around like 6.67 meters per second squared for the acceleration here, compared to the 4 meters per second squared over here. So why is that acceleration bigger intuitively? Right? It kind of seems a little weird. It seems like the same amount of force is being applied in both situations, which it is. What is different is the fact of this mass here existing, right? Whereas there is no mass over here. So the reason why there would be less acceleration is because this 100 newtons has to accelerate both masses, whereas this 100 newtons only has to accelerate this one, right? There's essentially less mass to accelerate, and therefore, for the same amount of force, there is more acceleration the less mass there is. Right? Because essentially, right, if A equals F over M, or whichever way you want to think of it, F equals M times A, right? If the mass goes down, and this is constant, the acceleration has to go up, right? So essentially in the first case, there's just simply more mass for the same amount of force, and so the acceleration decreases, right? So that's kind of the intuition behind it. And another type of problem AP Physics likes to throw at you guys is having you guys solve these systems without any numbers at all, right? So if you just had M1 and M2, you could have a question like, solve for the acceleration of the system in terms of all other quantities, right? This could be like physical quantities like G, could be like other forces like tension, sometimes other forces like maybe the force of gravity, but we can calculate the force of gravity more directly. So maybe, if anything, it should involve G, T, maybe the mass of object 1, and the mass of object 2, right? And we don't have to necessarily have all 4 of those, but they might show up in our answer. So again, I would probably take a system-based approach, sort of stretch this out horizontally again. Right? And treat this as a system. So, obviously we have tension forces. The force of gravity of object 2 would be applied to the right there, and we would essentially treat this as our system, right? So, acceleration of the system equals the sum of the forces over the mass of the system. So this is going to be, what is the only force that is external to my system? Well, technically again, right, I have the normal force and I have this force of gravity. But remember, these are going to cancel each other out in the net. So really all I have is this guy. That's going to be the force of gravity exerted on mass 2, which is going to be exactly m2 times g. The mass of the system is going to be m1 plus m2. So cool. Now what's really interesting about doing stuff like this is now you have what we call functional dependence. Meaning that we can see how acceleration depends on other factors, which is kind of interesting. So imagine that m2 is, something like 0.000001 kilograms, something extremely tiny, right? The acceleration of the system, if you think about it, would approximately be 0 over whatever m1 is plus 0, right? Intuitively, what would happen if m2 was extremely tiny? Well, we wouldn't expect the system overall to accelerate a whole lot, right? Because we know that the only force accelerating is the gravity on m2. If m2 is very, very light, we shouldn't expect much acceleration, and this is what the calculations bear out, right? If m2 is extremely tiny, we get an acceleration of a system which is essentially 0. Kind of do the same trick for m1, right? If m1 was extremely tiny, what would you expect? Well, if we go over here, right, if this guy is extremely light, he would be a lot easier to accelerate. So we might expect that the acceleration of the system would increase, right? What would it increase to? Would it increase forever? Well, let's see. We would get that this would be approximately m2 times g, whatever m2 is, and then we would essentially have 0 plus m2. Oh, that's interesting. Okay, so this is essentially m2 times g over m2, which these cancel out, and you get g. Does that make sense? Well, imagine, right, that m1 disappears. What happens to m2? m2 is essentially in free fall. And so if an object is in free fall, of course it's going to accelerate at g, at 9.8 meters per second squared, right? So this functional dependence actually gives us a lot more information about how all these things relate to each other. So anyway, I hope you liked Atwood machines. Keep in mind that you have choices, right? You can take things with this approach, and it totally bears out. You get the same answers. I'm sure a lot of you guys like this approach. It just feels a little weird to sort of stretch everything out like this to me. I like defining positive and negative directions and all that, and not changing which way gravity is pointing. But whatever floats your boat, if you like that, then go for it, right? You get the same answer. So hopefully this gives you some clarity on Atwood machines. Remember, always start with Newton's second law.